So last time we talked about inheritance as a way to inherit functionality from one class to another. Today we're going to talk about polymorphism, which is a way to leverage that inheritance to give our programs more features, more flexibility, more expandability, and just have general better design practices, which is something I haven't mentioned as much as I want to in lecture. I'll try to start mentioning it more moving forward, especially now that we have some OOP concepts. One of the big points of having these OOP concepts is to help you write code that's expandable, to be able to add new features to your code without redesigning your whole structure and everything that you've done so far. So to that end, lecture task 4, we're going to expand our point of sale project to enable modifiers to be added to our items. So in lecture task 3, you created the modifier abstract class. You extended that class in 3 other classes through sales, sales tax, and bottle deposit. So you had these 3 classes that all extend modifier. So they share functionality, they share methods, headers at least. The modifier has the price and tax methods that everything that inherits it has to implement. And we can add functionality. We don't for the project, but we could add functionality to the modifier class and have that functionality shared between all 3 of its subclasses, all 3 of the classes that extend or inherit from modifier. So we have that functionality with those 4 classes, and that's great and all, but why do we really care? Where we really get to start leveraging the power of inheritance is when we start using polymorphism, and that's when we write code that works with the type of the base class. So in our item class, we're going to write code that works with modifiers, and our item class isn't going to care what those modifiers are. And that's going to be a very powerful ignorance for the item class to have. So the item class can have sales added to it, applied to it as modifiers using the add modifier. We can add a sale. We can add sales tax. We can add a bottle deposit. But the item class doesn't have to know that any of those 3 classes exist at all. It doesn't care. All it knows is that it's getting some modifier. And since it's getting a modifier, it knows that it can call that modifier's price method to compute the overall price of an item, and the tax method, the compute tax, update price and compute tax method of the modifier to determine that item's final price and final tax based on all the modifiers. So in the item class, write a price and tax method. Write these methods that are going to apply all the modifiers to this item. So for example, the price method, each modifier has an update price method. So in your item class, you'll start with the base price of the item from the constructor and then run that through every single modifier in a loop, call update price on every modifier, and then whatever comes out the other end, that's your final actual price of that item. That's what you're going to get for that price. And it's important to not update the state. If I call price twice in a row, you should get the same exact price to apply all those modifiers. Some of those modifiers are going to be sales taxes and bottle deposits, which their update price method just returns the input, doesn't do anything, doesn't change the price at all. But it will still be called. That method will still be called because the price method is going to call every modifier's update price method. And then the tax method, call every modifier's compute tax method, and then add up all of the taxes. And a few things to note, just little things. I might mention these again at the end of lecture, but just to make sure it's clarified. The tax should add together. So if there are 2 taxes on an item, you should add the taxes, and each tax should be computed on the final price of the item, which is whatever price the price method returns. Tax does not, I've been working on the best way to word this without confusing people more, but you don't pay tax on tax that's been computed. So for example, if I have an item that's $10, and I have 2 taxes attached to that, 2 sales taxes, which are both 10%, I'm going to compute 10% on that $10 and get $1 of tax. And on the second tax of $10, I'm going to compute again on that $10, get another $1, and then my total tax will be $2. We don't compute the first tax, add that to the price, and then compute the second tax on 10% of $11. We don't do that. We don't compound the tax in that way. We don't like charge compound interest on the tax. So this is our goal for today's lecture task. Working with the modifier class without caring what the actual types are. Add modifiers, compute price and tax based on modifiers. The item class will not know or care what a sales tax is, what a bottle deposit is, and what a sale is. And that's the power of polymorphism. That's what we're getting at with lecture task 4. All right, so last time we saw inheritance, and we looked at the type hierarchy, and we saw that every single type in Scala extends this any class, and there are two basic categories of types in Scala. One, classes that extend any val, which extends any. These are what I call our primitive types. These are all the types that go on the stack as values. And then classes, everything else, everything that's not one of these specific types, everything else is going to extend any ref, which extends any. And these are the classes that go on the heap. The only thing that goes on the stack for these classes are references to these objects that are on the heap. So we can see right in our inheritance the difference between the stack and heap and how objects are stored in memory. Any val, you're on the stack. Any ref, you're on the heap. And any class that you write implicitly extends any ref. So if you don't extend any class, there's an implicit extends any ref attached to that class. So every class you've written so far, besides the LT3 classes, will extend any ref. So including your modifier class, your modifier abstract class, actually extends any ref implicitly. You don't have to type that code. It just happens automatically. So we have this is our inheritance structure. This is in this your class. In your class, we had our class that extends any ref, physics object, game object, extended physics object, and then we had a dodgeball and a health potion that both extend game object. And whenever we inherit this functionality, health potion extends and inherits. I'll use somewhat interchangeably, but health potion implements inherits all of the functionality of game object, so it gets all of its state and behavior. It has a location state variable. It has an object mass method. It has a use method that takes a player. It has a close to player method that takes a player. It inherits all of that behavior. Game object inherits all the behavior from physics object. Physics object inherits all the state and behavior from any ref, and any ref extends all of the state and behavior from any. So we get a lot of functionality in these classes without writing much code in these classes themselves, because we extend or inherit all the functionality from other classes. So that's what we talked about last time. Now let's start leveraging this and start talking about polymorphism. So we have a class that we've written, this health potion class, and this health potion class we say is a type health potion, and it is a type game object, physics object, any ref, and any. The health potion class and objects of type health potion actually have 5 different types. So whenever you have a class that extends another class, you're saying that class is that type. It actually is another instance of that type. So when I create a new health potion, that of course is a health potion, and I can store that in a variable or value, in this case of type health potion. I can give it to as an argument to a method that takes health potions and all that good stuff that we've seen with classes. But I can also do the same thing with any of its super types, any type that it inherits or extends. So if I create a new health potion and I want to store it in an object, a variable of type game object, well, that's perfectly valid too, because a health potion is a game object. A health potion is, by transitivity, a physics object. A health potion is an any ref. And a health potion is a any. So it is all 5 of those types simultaneously. Any health potion can be stored in any of these 5 variable types. It can, if I have a method that takes a physics object, I can pass a health potion to that object because a health potion is a physics object. It really is, because it inherits all of that functionality, and it can behave and masquerade exactly as a physics object. Yeah, you've been doing this with Fun Suite. So you're testing, you extend Fun Suite. So your test suite is a function suite, or Fun Suite for short. It really is a function suite. And then Scala Test, the library, which works with function suites, can work with your code because your code is a function suite, and it just treats it as a function suite. It calls its test methods that you've written and, does its thing. Or I guess that not that you've written, that you've added functionality to. But the library doesn't know what your test suite is. It doesn't know anything about it. It just works with test suites. The same as your item class isn't going to know what a sale is. It just knows what a modifier is. And then as long as you have a type that extends modifier, your item class can work with it. It's just the way the arrows work, Smeech. It's the way, the first people who developed OOP and started drawing these diagrams, they drew the arrows that way. I'm just going to stick with it. I'm not going to... yeah, exactly. Creeper has the link. It's UML syntax, the Unified Model Language, I think it is. That's the syntax that they use for relationships. The arrow points to the class that you're inheriting, not the inheriting class. So this is polymorphism. Like, I could just leave it at this. This is polymorphism, and then leave you to figure out all the implications of that. Like, why does that matter? Why do we care? What does that mean? This is polymorphism. When you have your interview next week and the TA or myself were like, explain the concept of polymorphism, this is it. Like, this is the whole thing. It's the fact that an object of a particular type can be stored in a variable of any of its subtypes. That's polymorphism. An object can pretend to be any of its types, any of types that it inherits. The name polymorphism comes from poly, many, morph, forms. Polymorphism is many forms. A health potion can take on 5 different forms. That's polymorphism. Yeah, you can clip that one, Lemon. That's this, and I'm surprised how often I'll have an interview and I'm just like, tell me what polymorphism is, and I don't get that answer. If everyone gives me that answer, I'll be super happy. All the TAs will be very happy in the interviews too. So, if you just say many forms, no. But if you explain this, if I have an object of a type and it's stored in a variable of a different type, polymorphism, baby. That's polymorphism. And then we'll ask you follow-ups, of course, and hopefully you actually understand the implications of that. But that is polymorphism. So let's talk about some implications of this and what we can do with this, why it matters, and why it is such a powerful concept that we're going to see throughout the rest of the semester, really. Even when we're doing functional programming, there are some aspects, some cases where we're going to use polymorphism, which is an OOP concept in functional programming. So let's talk about polymorphism. What are we doing? First, we actually have a pretty big restriction with polymorphism. So before I motivate this, I'm going to demotivate it. We have a pretty powerful restriction with polymorphism. And then you can only access the state and behavior of an object depending on the variable that's stored in. So you can only access the state and the behavior of the type of the variable that you're working with. So potion 3, for example, is of type physics object. Even though it stores a health potion, even though it's currently holding a reference to a health potion, we can't use health potion specific functionality, and we can't use game object specific functionality. We can only use physics object functionality. So this variable here can only access physics object functionality. So for example, the distance to player method, which we wrote in the game object class, When we have a variable of type health potion that stores a health potion, we get to call that distance to player method because the health potion class inherits that functionality from the game object class. Even though health potion itself, that class doesn't know about the distance to player method. It's defined in the game object, but that was inherited by health potion. That's inheritance from last time. In the game object class, since this class defines the distance to player method, if I have a variable of type game object that stores a health potion or a dodgeball, it could be storing, we can still access that distance to player method because it's defined in this class. So we have a variable of type game object. We can access the game object specific functionality, but we cannot access health potion specific functionality. So this health potion has a volume state variable, which is defined in the health potion class and doesn't exist in the game object class. So potion 2, we can't access the potion's volume through this variable because the variable is of type game object. When we move to physics object, we have a variable of type physics object. Remember, the distance to player method is defined in the game object class. So once we go to a variable of type physics object, we can no longer access that distance to player method. Because the physics object class, no matter how hard you look in the physics object class, you won't find anything called distance to player. You can look up its inheritance tree. You can look all over the place. You'll never find a distance to player method. And neither will the compiler. It's not going to find a distance to player method. So potion 3 is of type physics object. So this can only store a reference to a physics object, which has no way of knowing that a distance to player method exists. It happens to actually be storing a reference to a health potion which has a distance to player method, but that method cannot be accessed through this variable since the variable is of type physics object. So even though we have that functionality, it exists. Since we're storing this in a variable of one of the supertypes that doesn't know what that method is, we can't access it. A superclass is any class that you're inheriting. So health potion inherits game object. We say that game object is a superclass of health potion. So game object, physics object, any ref, and any are all superclasses of health potion. Did I put that on the slide? Maybe it was said in chat. That's superclass. That's what the superclass is. So physics object is a superclass of health potion. So from potion 3 of type physics object, or from potion 4 of type any ref, or potion 5 of type any, we can't access this distance to player method. If we go all the way up to the any class, we can't really access much functionality at all. We have a few base methods that exist in every single Scala class because they're defined in any. We'll talk about 2 of those later in today's lecture, the toString method and the equals method, which are called whenever we print something to the screen or when we say equal equal. Though that functionality exists for every single object in Scala. But we can't access any other functionality. We can't access any ref stuff if we store this in a variable of type any. We can't treat it as a reference. We don't get any physics object functionality. We don't get any other functionality from that. All we can do is those base methods. So we almost never want to do this, have variables of type any ref or any, but it is valid. It is something we're allowed to do. We can do that. Everyone good on this? No OOB is the only difficulty in LT2. The rest of it's not really new content. No OOB is the only new content that forces you to think about references. If you're struggling with no OOB, read my hint in the doc and study references. If you have a method in health potion which overrides a method in game object, calling that method in potion 2 would use the game object definition. It would use the health potion definition of that. So in game object, if we call the use, and this is part of the power that we get here, if we say potion2.use of player, we are getting, in this case, in this example, we are getting the health potion definition of the use method. And that's why we define, well, let me just click through some more slides. But that's why we define these methods in the game object class. So we're saying any game object has to have these methods. What actually happens when those methods are called is going to depend on what actual type we have in that game object. So here we have a game object variable, which actually is a health potion. We do get health potion specific functionality when we call methods that are defined in the, or declared in the game object class, like the use method and the mass method. But when we call those methods, we actually do get the functionality of the actual type that's stored in that variable. So that's how we can leverage this to get some specific functionality out of this. For example, in your item class, you're going to have modifiers stored in variables of type modifier or a list of type modifier. And when you call the actual update price or compute tax methods on those modifiers, you will get the functionality of whatever actual type is being stored, whether it's a sale, a sales tax, or a bottle deposit. You'll get the functionality defined in those classes, what we call concrete classes. You won't get the functionality from modifier because modifier isn't even going to have any functionality. So when you override a method, you are getting that functionality even when you store that object in a variable of one of its supertypes. You will get the overridden functionality. Can you override? Yeah, you can. So if I had something that extended health potion, I can override the method again and say, no. When I have an object of this type, this is what I want the method to do. So you can absolutely override a method that's already been overridden. You can override all the way down your inheritance chain. Yeah, you can't have two classes that extend each other. You'll get a compiler error because a compiler can't resolve what to do with that. So why do we care? Why would we ever want to? So all I did so far was demotivate this. Why would I ever want to store an object in a variable of one of its supertypes if all I do is lose functionality? What is the point of polymorphism? And here it is. Here's what we want to do. So if we recall the player class, which we talked about briefly at the beginning of last lecture, the player class had two methods. One method to use a ball, one method to use a health potion. To use a ball takes an input, a parameter of type ball. This should be dodgeball. I didn't update this one. Use health potion takes a health potion and then just calls the use method on the ball or dodgeball or health potion, passing a reference to the player to the method. This is going to get really tedious to expand when we want to make our game more interesting with more object types. We don't just want dodgeballs and health potions. Maybe we want my brain completely blanked on that one. Maybe we want like bow and arrows where you can shoot arrows at each other. Maybe we want melee weapons. Maybe we want poison potions that you can throw at another player. Yeah, knives, guns, cannons. Good suggestions in there. A speed potion to increase your movement speed temporarily. We might want a lot of different objects in this game. Every time we add a new object to the game, are we going to revisit our player class, add another method here, and then everywhere else in our code where a player can use an object, are we going to add specific code to call the right method in the player class? Well, of course the answer is no, because that's what we're going to fix. This is going to get extremely tedious if we have a separate class for every single item and we hard code all of our program, our entire game, to every single individual type of item that we can have. That's a pain. Nobody wants to do that. That really sucks. So we want to leverage inheritance and polymorphism to make it easy to add new object types, new game object types to our game. And to do that, we're going to modify our player class collapse these down into one thing, one method call, and just change this to a useItem method, which takes a game object. So we can store objects in any of its super types, variables of its super types. We can also do this across method calls. So we can have parameters of a super type and then call this method with an object of one of its subtypes. As long as this method is called with an object, a reference to an object that inherits game object, then that's a valid method call. And when we call item.use, we'll actually get the use method of the actual type of this game object. So if this is a health potion, this is going to be the health potion class's use method. If this is a dodgeball, we're going to get the dodgeball class's use method implementation. If this is a gravity coil game object, then we're going to get the gravity coil use method defined in that class. So this method call will have different behavior based on the type of this item. And as long as that type extends game object, this all works and it's all valid code that's going to give us our functionality. And this is why we can scrap if statements. We're not making decisions based on the value stored in a variable. We're making decisions based on the type stored in the variable. So this method with no conditionals has different behavior based on the type of game object that's given to this method. If this is a dodgeball, if this is a health potion, this method will have two completely different functionalities without using a conditional. So instead of this, and then having a method for each, we have 20 different game objects, we have 20 different methods. Now we have one method, and this also has the benefit of whenever we add a new game object, we're not changing, like it's not just the tediousness of writing a new method, but we're not changing the player class at all anymore. We're just adding new classes that extend game object, and player just handles them all the same. All is just generic game objects. So if we have our player class, and of course a lot more functionality, we have a lot more methods, and maybe this class is a few hundred lines long, we don't want to have to make changes to that, because when we change things, we have to re-implement, we have to retest everything that we've done. We have to run our unit tests again, hope everything still passes, make sure that change that we made didn't break this class. If we're not making changes to this class, we write our testing once and we're done. We don't have to write new tests for the new methods and make sure everything's working right. What a pain. We're just going to have this one method that leverages polymorphism to have different behaviors and have a lot more flexibility in this method. Now the game object abstract class, you might have asked yourself, why would we even define these methods in the game object class? Why would we even declare these if we don't define them? We don't give them functionality. Why not just leave it up to health potions and dodgeballs to implement those methods? Like, why do they even have to exist in the game object class if they don't do anything? This is why. So we can't access through this item variable. We can only access game object specific state and behavior. We can't access health potion and dodgeball state and behavior. So if these methods only existed in dodgeball and health potion, we can't do this. We can't call the use method in the game object class because it wouldn't exist. So we put the use method in the game object class, and the object mass method in the game object class to say, hey, if you extend this type, you have to implement these methods, because now when a player has a game object, you can guarantee that it has a use method. It's guaranteed because it's defined in this abstract class. And this abstract class was saying, hey, if you extend me, you have to implement use. You have to do it because I'm giving a guarantee to anybody who has an object of my type that that method use exists. And that's why we have these abstract methods. It's so we can leverage polymorphism So players can have game objects and guarantee that they have a use method, guarantee that they have an object mass method, guarantee that they have a location also for this for our purposes here. So we have these abstract methods to guarantee that we have what we call an interface or an API that we can call. So we're effectively defining an interface. This is how you can interact with game objects. And those methods will do stuff at some point. Some point these will be defined. We have that guarantee, and we can just rely on that being a thing. So in your modifier class, you have two methods declared but not defined. You have the update price and the compute tax methods. In your item class, you can guarantee that you can call those methods and they'll have some sort of behavior. You just don't know what that behavior is going to be, and you don't care. Whatever the classes that extend modifier, their job is to implement those methods and make those methods do things. But in your item class, you just care that you have modifiers. They're going to do something. They're going to have these two methods that you can call. And you just don't care what they do. And then you never modify the item class again. Even when you're doing the application objectives and adding more modifiers that have different behavior, you still don't modify the item class. The item class just cares that it has a modifier attached to it, and that's it. You can access the health potions functionality through a game object variable, but only through the interface of a game object. So you can only access location, you can call object mass, and you can call use. That's it. So if there's some health potion functionality you want to take advantage of in the health potion class, you have to have a way to access it through these two methods. Like health potion has, what does health potion have? Health potion has a volume. In our player class, we can't access the volume of a health potion at all. But we can call the object mass method, which gives us the mass of the health potion, which is derived from the volume of the health potion. It's the volume times 7 in our code. So we can get a measure of something that's affected by the volume of that health potion, but we can't just say item dot volume. That's not gonna compile. The compiler's gonna yell at us. Outside of game dev, when is polymorphism useful? Like everywhere. In GUIs next week will be the first. Actually, in states on Friday we'll see another example. But in GUIs, so a button on a GUI has an action listener attached to it. And when you click on it, the action listener has an action method. I might be messing up the names a little bit there. Has an action method that is called when the button is clicked. So if we create a class that extends action listener and we implement that action method, we override the action method and attach that to a button, we can have whatever action we want to occur when that button is pressed. And you can look at the handout code. You can see that in I don't know if I extend that. Do I? Maybe I do. I forget exactly how I set that one up for this project. Yeah, like an event listener. They're called different things in different libraries, so I might be mixing up what I'm calling it. But it's listening for the event that's triggered by the pressing of that button. We do that through OOP, through inheritance, through polymorphism. You extend event listener, override its whatever is called when the event occurs method, and then attach that to our GUI element. And then when that event occurs, the GUI element doesn't care about our class, our type, but it cares that it has an event listener. It'll call its method that's called when the event occurs, and then that functionality will be whatever we overrode that method with. That's what's going to happen when that event is triggered. So yeah, I've been realizing I'm a little overloaded on the game examples over the past few weeks. But yeah, this is absolutely applicable outside of games. Games, I'm just trying to use something that's I don't know, hopefully makes more sense, but if you don't play many games, it might make less sense. Yeah, game examples help a lot of you, but some of you it does miss. So I will switch it up and start doing non-game examples. But there is one more on Monday, a pretty big one. Okay, so now with our use item class, we have our multiple items that are game objects. We have a player, and the player can use either of them, even though it's a dodgeball and a health potion. We can still call the use item method because use item takes a game object, and a dodgeball is a game object because it inherits game object. It extends game object. Health potion, same thing. It extends game object, so it is a game object. So we can safely call use item on a health potion, even when stored in a variable of type health potion, because we have this implicit assignment. Item of type game object equals potion, which is a health potion. It's a valid assignment because a health potion is a game object. Polymorphism, baby. Polymorphism. But wait, there's more. Yet again, last time we had game object. Ooh, this should be physics object. We had game object extend physics object, so that we can have physics applied to our game object. Every game object, health potions, dodgeballs, whatever else we come up with, gravity guns, we don't care. They extend game object, and game object extends physics object, so we can have physics applied to all of these objects in our game without even giving a crap about physics when we write the code for those objects themselves. When we write our gravity gun class, we extend game object, and we only care about writing gravity gun specific code. We can stay focused on the task at hand without worrying about how does this interact with my physics engine, how does this interact with my players and everything. You just build the game functionality. You just focus on what do you want a gravity gun to do in your game. And that's one of the huge advantages of this. You stay focused. You have your code separated into functionality where you're focused on the code you're writing right now. So we can also do the same thing with our player. We want physics to apply to our player as well. This should say physics object, but we can have I changed it up here. We can have our player extend physics object, and that's it. Physics applies to our player too now. To really get that to happen, let's see an example. Now, there's no physics engine code. There's no physics object code. I did update this example in the repo right before lecture, so I did write those classes with just comments that say physics not implemented. But so you have to use a little imagination that we actually wrote a physics engine. We're not writing a physics engine because they're still running the physics engine assignment in the other section, and I don't want to leak solutions. But there was a physics engine assignment. At this point, you'd be working on physics engine. You'd be writing your own physics engine. And then this example would say, hey, that physics engine you wrote, bam, you can use that physics engine for this example. So just imagine you had that amazing moment in your life. So since all of these are type physics object, now player, potion, and dodgeball, these are all of type physics object because they all extend physics object one way or another. Health potion and dodgeball do it indirectly by extending game object, which extends physics object. Player extends physics object directly. They're all of type physics object, so they can be stored in variables of type physics object, but they can also be stored in data structures of type physics object. Which again, for your lecture question, you'll have to have some data structure of type modifier in your item class to store those items. Not to give away the solution, but you need a data structure of modifiers. Since we can store these in variables, these act as the type of any of their superclasses, we can have a data structure of physics objects, and we can mix types. This is something we took for granted last semester. In Python and JavaScript in 1.15, you just take that for granted. I can have a list of any type I want. Why wouldn't I? Why would it be any different? Why wouldn't I be able to do that? With a strongly typed language, you have to specify the type of the list. But if that type is one of the superclasses of multiple different types, we can store different types in the same data structure if all of those types inherit the type in the data structure. Yeah, polymorphism should be nerfed. It's a bit OP, but we're going to take advantage of this until they patch it. So these items of different types can all be stored in this data structure because this data structure takes physics objects. Player is a physics object. Health potion is a physics object. Dodgeball is a physics object. Mix them all together, throw them in one list. Perfectly valid code. If we have a physics engine that takes a list of physics objects, we can throw all those objects in there. The physics engine does not care that this is a player, 2 health potions, and a dodgeball. Does not care. It's just going to do its physics engine stuff that it does to physics objects. Doesn't care about anything else. Doesn't care about the rest of the functionality of these. So the extra functionality that the physics engine can't access because it can only access physics object functionality is what we add to these classes to have our game logic and our actual game doing game stuff. Players throwing balls, players gaining health. The physics engine doesn't care about any of that, but our game does. So we're storing these in a data structure of type physics object, but we still keep references to these objects of the types that they actually are. So I can still say player dot use item potion 1 somewhere else in my code and still give all these physics objects to the physics engine in another part of my code to apply physics and get all the functionality of my classes. So just because we have that restriction doesn't mean we have to say health potion equals potion of type physics object and lose all health potion specific functionality, because we're going to keep those references at the level that we need where we need it. So here we want to do health potion stuff. We're going to store it in a variable of type health potion. Here we want to do physics engine stuff. So we're going to store these in a data structure of type physics objects, because we don't need the other functionality, but we want to leverage polymorphism. So we write this physics engine once. When we write this physics engine, we don't give a crap about health potions and dodgeballs or whatever else is going on in this game. We just care about physics and vectors and things like that, and moving things around and updating velocities and all that good stuff. We don't care about this health potion heals a player. But over here we do, so we're going to store it in a variable type health potion. Physics object isn't really implemented. I do have it as a concrete class, not abstract. But it would depend on what we want to do with that and what we do down the road. Just the rest of our implementation. If we actually implement the physics engine, what it would be. So health potion has 5 different types. This is polymorphism. We saw some implications of this, but what else can we do with this? So much we can do with this. We're going to see the state pattern starting Friday, which is one application of polymorphism. This idea that we can have variables, objects of one type stored in variables of another type. We're going to see more applications of that with the state pattern on Friday and next Monday. All right, and any questions on polymorphism? I just got a quick override. Quick talking about override, kind of shifting back into inheritance a little bit as we digest polymorphism. That's your intro to polymorphism, which we'll reinforce over the next 4 lectures, really. We'll be talking about polymorphism, all the implications of it. Actually, 6 minutes left. Let me get through override. So override, we saw this a little bit. We overrode functionality in a class that we controlled. Now let's override some functionality in a class that we don't control. So any and any ref have functionality in them, and your classes always inherit any ref, which inherits any. So you get all of the functionality from any and any ref. Any includes a few methods, and any ref has a few methods that we're going to that we can take advantage of. We'll talk about 2 of them right now: toString and dot equals. So toString, you can call directly on any object. You can say dot toString and convert that object to a string. This is also called implicitly whenever we print something out. If we call println of something, what println does is calls toString on that object and then prints that to the console. So println takes an object of type any, or reference to an object of type any, So it doesn't matter what we give it. It can take literally anything in Scala, because everything's an object and everything extends any. So it can take anything, and then it will call the toString method, which it knows exists because it's defined in the any class, which is inherited by everything. So println calls toString, and there is a toString implementation in the any class, which gives us this default behavior of the object type, the @ symbol, and then a reference to that object. So if I run this code, I'm going to get something like this: the fully qualified name, which is the package and the class name, @ and then some random whatever. These numbers will be different each time, and each time you run the program. They don't really mean much to us, but this tells the JVM where in RAM, where in heap space to find this object that's being referred to by this variable. So potion1, remember, it's just a reference. So in that reference, here's the information of it. There's not actually a health potion stored in the variable potion1. It's just a reference to a health potion on the stack, or on the heap. So we create a few health potions. We're going to assign potion1 a new variable, I should say of type health potion here, potion3 to potion1. Print them all to the screen, and we'll see that potion3, this is a way we can check our references. Potion3 actually refers to the exact same potion as potion1. Those variables store the same reference, or references to the same object. And then we have the .equals method, which is called when you do ==. So == will call .equals, and the .equals method is going to return true or false, a Boolean. Are these two the same? Are these two equal to each other? The default behavior for == is to compare the references of the objects. So these two health potions to us are identical. They're at the same location. They have the same volume. Everything's identical with these two health potions. But when we say potion1 == potion2, which calls the .equals method, which compares the references, we're actually going to get false, because these two potions refer to different health potions. So the default behavior of the equals method is to compare by reference. These references are different, false. These are not equal. Potion1 and potion3, which do refer to the same object, that's going to return true because the references are identical. This is how we're comparing the reference values. The default equals method, which is called by ==, that's comparing by reference. This is saying, do potion1 and potion2 refer to the same object in the heap? That's the default behavior of the equals method. Yeah, and if you drink potion1, potion3 disappears, gone. Make sure potion1 and potion3 aren't both in your inventory. So we can change this behavior. Those two behaviors usually aren't what we want. We want something more meaningful to our application. So let's go to the health potion class and the physics vector class in this case and override that functionality. So we're going to override whatever we got in the toString method, which is printing out the fully qualified name and then @ the reference. We're going to override that functionality and give it whatever we want. I want to print out the location and the volume of this health potion. Location is a physics vector, so when I concatenate this, treating it as a string, the toString method of the physics vector class is implicitly going to be called. So I'm going to override that toString method too, so I don't get this.location physics vector at some garbage. I don't want that. So I'm going to override the physics vector toString as well to print out a vector in the way that we expect vectors to be printed out. Parentheses with comma separated values. We can also override the equals method in a similar way. Here I'm going to use a match case statement, something I don't think we want to talk about too much right now. You got enough to digest with polymorphism. But suffice to say, this is going to have different functionality based on the type of the input, the type of object in this case. So the equals method always takes something of type any, and we use the match case statement to check the type. We're going to say if we're given a health potion, then say these are equal if they have the same volume. We're going to check these the volume of these. And if it's not a health potion, if it's any other type, return false, where underscore is a wild card in Scala, like a star in other languages. And yeah, Scala really likes arrows. Scala loves its arrows. So with this behavior, we're going to say a health potion is equal to another object if it's a health potion with the same volume. Otherwise, they're not the same. Now we rerun this code. This code doesn't change at all. We just overrode some methods in the physics vector and health potion classes. And now we get completely different behavior. We get our potions printing out with some more meaningful information that actually reflect the state of that health potion, not just where is this on the heap, which is something we as programmers almost never care about, at least at the level we're coding right now. And then when we check if these potions are equal to each other, this is now calling the overridden equals method, which is comparing their volumes. If they're the same volume, we're going to say these are effectively equivalent. So now potion 1 and potion 2, referring to two different potions, are going to be treated as equivalent because their volumes are the same. So that'll be true. And then potion 1 equals potion 3 was still true. Yeah, why would you want to compare references? You usually don't. For most applications, you wouldn't. You should be tracking your references. You should be aware of how your references are moving around. But you usually don't need to compare them unless you're writing unit tests that needs to ensure that the references didn't get messed up. Which brings us back to the lecture task. So you're adding functionality to the item class to leverage the fact that we have 3 classes that extend modifier. And then in the item class, we're only working with modifiers through polymorphism. We don't care what type is actually stored in those modifier variables that we're given when add modifier is called. We get a modifier. We don't care which of the 3 subtypes it actually is. We're just going to treat it like a modifier and leverage polymorphism to call its update price and compute tax methods.